Good morning. All right, are there any questions? Any questions? Okay, let me just mention something before I start on the new material. If you remember last time, we looked at the end of the hour, we looked at two CSTRs in series. And we went through and we solved it for the case of where the CSTRs were the same size and where they were different sizes. We did all that algebra, and then at the end of the hour I mentioned that, something interesting. I mentioned that when we did these plots, so where this is time, so here's 0, and this is CA in. So we have a step change in CA in. And then for CA1, and here's CA2, for CA1, instead of a step change, we saw that we had a 1 minus an exponential solution that asymptotically went to the limit. And for CA2, we saw something different. So again, the assumption was for t less than 0, they were all at steady state. And here we saw that instead of having a break in the first derivative in slope, we had a break in the second derivative. So the curve looked something like this. And what I mentioned was, if you notice here, CA in undergoes a step change. Here, CA1 doesn't go a step change, undergoes a step change, but the derivative of C with respect to T undergoes a step change. And here, the second derivative undergoes a step change. And I mentioned that you can take the full equations and take the derivative of dCA2 dt at t is equal to 0, and show that it's equal to 0. And I asked you to do that for homework. Let me just mention here's sort of an easy way of seeing that, although I still would like you to do that for homework. If you notice, here we have the equation for CA2, which I didn't change from last time. It's still up on the blackboard. And for t less than 0, if you remember, for t less than 0, this is 0. The system is in steady state. So for t less than 0, we solve this equation. We set the CA2 dt equal to 0, and we solve this for CA2. We did that last time to get the steady state value. Now, let's see what happens in this case as soon as we introduce the step change. If we introduce this, so first of all, what we know is for t less than 0, there's nothing to write here. This is a listening thing, not a writing. For t less than 0, CA2 is the value of CA1 divided by tau 2 times t2. Well, what happens when I introduce the step change? When I introduce the step change, CA1 doesn't change. CA didn't change. Initially, only the derivative of CA1 changes. So the value of CA1 at t equals 0 is the same as it was a millisecond before. So since CA1 hasn't changed instantly at 0, this is still equal to this, because this is the same value where it balanced previously, for t less than 0. So if these two are equal at t equals 0, then dCA2 dt is equal to 0 at 0. Of course, after t equals 0, it's not 0, because after t equals 0, CA1 has changed. And if CA1 has changed, these two no longer balance, and the difference is going to give you dCA2 dt. So that's how you can just see it directly from the governing equations. And you also get a sense from this equation that I could also write, if you remember, we also have the equation dCA1 dt plus CA1 over T1 was equal to CA in over tau 1. And I want you to notice that a change in CA in affects the derivative of CA1, not CA1 directly. So this change changed the derivative. Similarly, a change in CA1 in the derivative of CA1, a change in CA1 itself doesn't affect the CA2 dt. But if I take the derivative of both sides, the second derivative here plus the derivative gives me the first derivative of CA1. The first derivative of CA1 has changed, so therefore the second derivative of CA2 is changing. So this is all a little bit of mathematical analysis, a little bit stuff that they don't bother with in the textbook. But I think it's sort of nice to be able to look at a simple equation like this and learn that much from it. Are there any questions? So that's just sort of an addendum, a postscript to what we did last time. So it's really part of the last lecture. Are there any questions? Okay, if you notice, someone else actually had the nerve to use this room. I thought it was going to be our room. And the one thing they erased was the part I wanted to keep. Everything else they left on the blackboard, except this, and they drew some sort of funny picture there. They must have known that that's the part that I wanted out on the blackboard. Okay, well, we've looked at CSDRs. Now let's look at another situation and the simplest type of control involved. And that's called bang-bang control. Funny name. And what's the idea of bang-bang control? Bang-bang control is basically the heating system in your house probably works on bang-bang control. And what does that mean? It means the controller is really simple. When the temperature in the house goes below a certain value, it turns the heater on. And then the heater stays on until such point that the temperature goes above another cutoff, in which case it shuts the heater off. So the idea of bang-bang control is Q of the heater is equal to, well, if I've got T less than T min, then it's equal to some value. Let's call it QH star. If it's greater than T max, then it's equal to 0. And if it's in between T min and T max, there's no change. So you can imagine if I looked at bang-bang control, typically this is Q of the heater. And if this value is QH star, and this is time, you can imagine that there's going to be a certain amount of time when the heater's off, then it's going to be on for a while, and it's going to shut off, and it's going to be on for a while, and it's going to shut off, etc. Now, whether these should all be the same height. And that's pretty much how the heater in houses works. There's no reason for a fancier heater, usually in most houses. Now, of course, you don't want T min and T max to be too close, because then the boiler is constantly going on and off. And the more you switch it on and off, the more likely it is to break. So let's look at a situation where T min is, say, 17 degrees C, and T max is 23 degrees C. So you got 6 degrees centigrade. That's not too bad. That's around 10 degrees Fahrenheit, and that's okay. And that way, you don't keep turning the heater on or off too often. And what we'd like to do is take a house, and we'd like to do a heat balance on the house. And so let's make some assumptions. So we're going to assume that the air in the house is well mixed. So T in the house, T with no subscript or superscript is in the house, is the same everywhere, is uniform. And I don't want to use T, I'm going to use a script T, because I've been using T for time constant. So where T is the temperature in the house. Someone trying to break in here? In-house. And let's make T out be the outside temperature. And if it's the winter, that could be really cold. In the summer, you don't usually need your heater. So we would make T out to be the outside temperature. I shouldn't use T here, I should have the outside temperature. And I'm going to assume that there are no leaks. So the only heat that leaves the house leaves by conduction. There are no leaks. So only heat loss by conduction. And I'm writing too small again, so let me start writing a little bigger. Although I think the picture of the house is big enough. And we're going to be given CP hat, CV hat. The hat means per unit volume. Hat means per unit volume. And we're also going to be given UA, where you've all had unit operations. Is that correct? So UA, you know, U is the overall heat transfer coefficient per unit area, and A is the surface area of the house. Okay, so why don't we do a heat balance? And I'm going to assume that certain things I can ignore. So I'm going to assume I can ignore that the, let's see, the kinetic energy, the potential energy, and the shaft work are all negligible. So assume kinetic energy, potential energy, and shaft work all negligible. Negligible when I do my mechanical energy balance. So I'm going to do the mechanical energy balance. So why don't we go through it? So therefore, I've got the UDT, where U, that's a bad, this is the internal energy. So I need to have a different symbol. What did I do in my notes? The symbols of U. Well, I'm just going to I'll use a word instead of internal energy. ET is equal to Q minus W. And there really is no work, so there's only heat loss and heat gain. Heat gain from the heater and heat loss through conduction. So, so in particular, there's no convection because there's no convective heat transfer because I'm assuming there's no leaks. So if I write this, I have rho CV hat times the volume. Usually it's rho CV dt, but CV is per unit volume, so I need to multiply it by V to get the total CV of the house. dt is equal to Q minus W. And we said we can ignore the work. There's no work here. So Q is the heat loss. So it's negative minus UA T minus T outside. And then T strict T outside plus Q heater. So is that clear? This is the ddt of the internal energy, rho CV dt, where CV is CV hat times the volume. And this is the heat loss by conduction. And this is the heater, the boiler. And you know what the boiler is doing? It's doing this. So why don't we go through and do the problem? Are there any questions so far? Remember, feel free to ask me questions. If I do something you don't understand, just ask. If you basically learn the material in class, it makes it a lot easier later.
So E internal EN, that's energy, right? But
internal energy.
And that's not enthalpy, right? That's different than enthalpy.
No, enthalpy is H. So this is what you in thermodynamics call U.
Okay.
or what physicists call capital E. Chemical engineers call it capital U. Physicists call it capital E. It's what appears in the first law. And the reason I'm not writing a U is because I already used U for heat transfer coefficient, so I don't want to confuse you with the same notation, meaning two different things. I'm sure I do enough to confuse you, so that I can at least try to avoid. Other questions? Okay, so let's notice I have a minus sign here because it's a loss. So the thing with the t has a minus, I bring it to the other side of the equation. I've got rho CV hat v t dt plus UA t is equal to UA t out plus Q. So all I did is I moved it to the other side of the equation. And now what I'd like to do is I'm going to divide by rho CV v. And here things cancel. And notice this is of the form I'm used to. This guy has to have units of inverse time, because this is temperature over time. Temperature has to be over time. So this is my time constant, which I'm going to call T1. That's why I'm not using simple T's for, and I should make all these script. So I want to use the script T's for temperature and save the capital T's for time constants. So this is my time constant T1, and this is, which we said is just 1 over A in this notation, and this thing is B. B. And you can notice that A is just a bunch of constants, and B, there are a bunch of constants here. I'm assuming that the temperature outside doesn't change. So let's assume that this is constant. The denominator is a constant. The numerator is sort of a function of time. But what I can do is I can treat each of these periods from, say, T1 to T2. I can just, if I do just that problem from T1 to T2, Q is a constant. If I do only the problem from T2 to T3, Q is a constant, 0, etc. So I'm going to do this as a bunch of problems when the heater's off and when the heater's on. That way I can consider B a constant. I just have many problems instead of one problem. But they're all the same problems. Is that clear? Okay. I don't know about you, but the last thing I was thinking of this morning was a heater. The humidity just kills me. I can use air conditioners. Actually, the air conditioners kind of nice in here. Any questions? Okay, so now let's go ahead and solve the equation. I'm going to solve it in general, leaving QH in there, and then we'll look at the special case QH is constant, positive, and QH is 0. Okay, so if I can consider A and B constants, here's my solution. So I have T of T, and this is saying, right, for any one of those, and this is for T between Tj and Tj plus 1. So it's important. It's not one solution everywhere. It's a different solution for each. It's a different solution for each time interval. Okay, so this is equal to T of the initial value. So T at Tj, times e to the minus T minus Tj over T1 plus B over A. Well, let's look at B over A. When I take b over a, well, when I take this coefficient, I divide it by this coefficient, I just get 1. So I have t out. Plus QH divided by, well, when I divide by this, the rho CV over V cancel, and I just divide by UA. Times 1 minus e to the minus t minus tj over t1. Yes?
Sorry, I missed. Why is that T1 equals 1 over A, not just A?
Because A is, you're right, it's 1 over T1, and it's equal to A. Thank you. My mistake.
Okay. I think I still don't follow the.
Well, A is the thing multiplying the variable. A is multiplying Y. And A, we said, has units of inverse time, because it has to have unit temperature over time. So that's why I call its inverse, the inverse of A, a time constant, T1.
Oh, okay.
And that's because T1 appears, well, A appears here in the exponents. So A is 1 over T, as you can see. And we discussed last time how this characterizes how fast the exponential decays.
Okay, got it. I was confused by the T variable meaning time now for temperature.
I know, that's why I'm trying to be consistent and use the script T for temperature and the big T for a time constant.
Okay, thank you.
But no, I know that's confusing. That's what sometimes there are problems where I'll have a third temperature and I'll use theta as another thing that would naturally be a T. You know, you have too many T's here. It's like a T shop. Okay, so let's see what we get here. So let's notice what happens and let's see if I want to put this in another form. Okay.
I'm just a bit confused on where did you get the TJs from? Like, what do they stand for? Is it the same as the
TJs are the times that the heater either shuts on or off. So I have them listed here. So at T1, say the heater goes on. At T2, it goes off. At T3, it goes on. At T4, it goes on. So it's just the times in which that I either hit T min or hit T max. Temperature min or temperature max. Okay, so the first thing to notice is let's look at our time constant. The time constant, that is how quickly the system responds. This is how quickly it responds. Here's the physics. The time constant, look at the parameters it has. It has rho, V, CV. These are all characteristics of the house. And UA, which is a characteristic of the house. Notice the time constant does not depend on the heater. It does not depend on the heater, the time constant. It depends on the characteristics of the house. It also doesn't depend on the outside temperature. So the time constant, T1, does not depend on the heater and does not depend on the outside temperature. It's solely a property of the house. It's how the house responds to different inputs. Okay, and let's look at what happens here. So let's imagine that, let's start over here. So at TJ, the heater was off. At T1, let's look at J is equal to 1. So at J is equal to 1. So T1, the heater switches on. And in particular, the temperature in the house is cold. So T at T1 is cold. I'd like to heat it up. So, okay, let's notice what happens here. I thought I wanted to put it in a different form. Yeah, let's put it in a slightly different form. Let's put it in a form, let's subtract T out from both sides. So I'm going to subtract T out from both sides. So I have T minus T out is equal to. And why do I do that? Well, I do that for the following reason. When I subtract T out, then that's moving one of these terms to the other side of the equation. So So let's see what I have. So I have a QH over UA times 1 minus e to the minus T minus T1 over T1. And then I have TJ exponential minus T out exponential. Okay, so let's see what happens here. The outside, T1 is cold. So at time 1, the temperature in the house is cold, but it's not as cold as it is outside. It's even colder outside. So this thing is negative. Okay, but that says that the temperature minus the outside temperature, if this were the only thing going on, would continue to decrease. And that's true. If it's colder outside than inside, and the heater is not turned on, then the temperature will continue to go down. And in fact, if I wait for infinite time, let's see, is this the right form? Let's just see if it looks right. Okay. Yeah, that looks okay. Just 1 second, I'm thinking. Yeah, okay. So let's look for 1 second. I'll answer your question 1 second. Let's just look at this equation, and let's just see what happens at infinite time. So if the heater is turned off, if we turn the heater off, and we look what happens at infinite time, we could actually also look at it here. Let's just look at it here. If the heater is turned off, so QH is 0, and we go to infinite time, where T minus T1 is infinite, so we no longer turn the heater on. The heater is destroyed. Then this goes to 0. So the whole right-hand side is 0. So that tells me that T minus T out is 0. So as T goes to infinity, with broken boiler, then T of infinity goes to T out. Which makes perfect sense. If the boiler's broken, then eventually this inside the house is the same temperature as the outside of the house. There was a question. Yes?
Yeah, in your original equation, you have T as time constant, T of Tj.
Oh, this is a strict T.
Oh, okay,
Thank you for pointing that out, because I tend to do that all the time. Confuse notation.
But that's like without accounting for the insulation.
I'm sorry, can you please?
That's like without accounting for the insulation and all that stuff.
No, no, the insulation is in U. UA has the insulation, and I was just about to comment on that. So let's notice that if I put more insulation in, I decrease the overall, overall heat transfer coefficient, UA. I decrease U. If I decrease U, what do I do to the time constant? If I decrease U, I decrease A, that means I increase T1. Makes perfect sense. If I put more insulation in the house, then the time constant, the amount of time it takes for the house to cool down when the heater's off, is longer. That's because I have more insulation. So it makes perfect sense. Other questions? Okay, well, let's see what this looks like. So we say this thing is lowering the temperature of the house, because this is negative between T1 and T2. But this thing is heating the house up, because this is decreasing and this thing is positive. So 1 minus something decreasing is something that's growing towards 1. So this is growing towards 1 and this is positive. So what happens if I plot this? So here's the Q heater. And here's the temperature of the house versus time. So here was a certain value. And and the outside temperature is say way down here, out, and this is T1. Well, now it's going to start going up. And because it's 1 minus an exponential, it goes up like this. Exponentials go like this. Minus exponentials go like this. And if I let it keep going, it's just going to keep going until it reaches a very high temperature. It will eventually level off because eventually the heat from the heater will balance. Eventually the heat from the heater will balance the heat loss. But that could be way above 23 degrees. That could be at 40 degrees centigrade. And you don't want to sit at 40 degrees centigrade. I've been in 50 degrees. You don't want to be in 50 degrees centigrade. 50 degrees centigrade is about 120, 121 degrees Fahrenheit. Okay, so now I get here, and what happens? The heater goes off because I've hit 23 degrees. So this is say 23, and this is 17. Now what happens? Now all of a sudden QH becomes 0, but the equation stays the same because I did it for any QH. Now all of a sudden QH is 0, and here's my solution. And now what happens is that the amount that the temperature exceeds T out starts to decrease exponentially with a time constant T1. So during this next phase, T1, T2, T3, it's the same solution but with QH equal to 0, and now I have an exponential decay. And if I let it go, this exponential decay, if the heater were broken, would go down to T out. But I don't want to do that. I don't want to sit in the house till it's 10 degrees Fahrenheit inside. So I turn the heater back on. So at T3, the heater goes back on. And now I go the same solution, but now QH is QH star. So it goes back up. T4. Etc. T5. 6, etc. So here it goes back down. It goes back up. And this is bang-bang control, because bang it goes on, bang it goes off, bang it goes on, bang it goes off, etc. Are there any questions on that?
I have a question. I'm just having trouble seeing mathematically how you.
I'm sorry, when you give me,
Yeah,
I hate to violate COVID rules, but I would like not just me to hear the question, but everyone to hear the question.
I'm just having trouble seeing mathematically how you subtract T out from both sides of the equation at the top.
Oh, okay. So on the left, it's easy, right?
Mm-hmm.
The left side, I subtract T out. This is T out times 1 minus an exponential. And I leave this term alone. This term I just copy. So I have T out times 1. I throw that one away. And then I have T out times the exponential with a minus. T out times the exponential with a minus. And here I have Tj times the exponential with a plus. And I kind of like this form because it, separates out QH from T out. Here they were kind of mixed together. And here there's the QH, the heater term, and just the house without the heater. So that's kind of why I liked it. I mean, I could have reasoned it all from here, but I think it's clearer from this equation. Other questions? Okay, so now we've done two situations where, and I can erase this stuff from last time. All this stuff we had on the blackboard last time, so there's no reason to get up there. Okay, so this is great. Whenever we have a linear first order differential equation, we don't have to do much work. We just appeal to the solution and we copy it from here. Easy. Unfortunately, real life is usually not linear. So let me give you an example. Let's look at a CSTR. Where I have a reaction, 2A goes to B. if I have a rate constant K, then the rate of destruction of A, or the rate of production of A, is minus 2K CA squared, if it's mass action kinetics. I assume you've had this already in your kinetics class. K is the rate constant, comes down. It's negative because it's on the left side of an arrow, on the tail side of an arrow, not on the head side of an arrow. That is, it's being depleted. It's CA squared because it's mass action kinetics, because I'm picturing two A molecules banging into each other to react, so I need two of them. And it's just a convention to put the 2 in here, to put the stoichiometric coefficient. I could absorb the 2 into the K, but this way it's the same K if I want to write RB. So if I write RB, that's just K CA squared. So if I include the stoichiometric coefficient, I can use the same K for both of them. Well, notice this is nonlinear. If I put this into a CSTR equation, the rate equation is not linear. I have CA squared and not CA. What do I do? Let me give you another example. Let's say I have a CSTR with heating, with a heating and cooling port. Cooling. And if the temp gets,
Are they the same case, or do they have different cases?
I can't understand it.
So when you're doing RV, do you do the same
RV?
RV?
RV, yes. They're the same K. That's the same K. That's why I include the stoichiometric coefficient here. Here the stoichiometric coefficient is minus 2, and the minus sign is because it's on the tail side of an arrow, and the other stoichiometric coefficient is plus 1 because it's on the head side and the coefficient is 1. And that way without thinking, I can use the same K all for everything on both sides of the equation. That's sort of a standard convention in kinetics. You don't have to do that, but then you still have to remember that the coefficient here is twice as much as the coefficient here. If you do it this way automatically, you don't have to remember that. It's just automatic. Okay, so let's notice that in this case, I have some sort of reaction going on here. And the reaction might depend on temperature. If the reaction depends on temperature, if K is a function of temperature, that is typically K can be written as K0 e to the minus activation energy over KT. That's clearly not linear. If I have a flow system where, another example is if I have a flow system, if I'm a flow of a gas that depends on temperature, so I have an input and an output. So I have a volumetric flow rate here, V in, and I wanted to do some sort of heat balance on what's going on in here. If I change the flow rate of the coolant, the flow rate of the coolant here will affect what's coming in here, because I've got a volumetric flow rate times. So for example, I would have a rho VCP times T minus T reference is the H in, where H is the enthalpy. So notice that V that actually enters here will depend on the flow rate of the coolant. So, and also the temperature will depend on the flow rate of the coolant. So both this and this depend on the coolant. And since they're multiplied by each other, that's nonlinear. So what do we do when we have nonlinear? What do we do when we have systems that are nonlinear? Do we jump out the window? I don't think so, not unless we're on the ground floor. The problem is, in general, whereas in general we know how to solve linear equations, like this one, we don't know how to solve nonlinear equations in general. Sometimes you can get lucky and solve it, but many times you're stuck solving it numerically. So, or what you can do is you can make an approximation. And the approximation is called linearization. And we're going to make extensive use of linearization in this class. What is linearization? Let's look at it in graphic. Let's say I'm looking, say, at the rate as a function of concentration. RA as a function of C from this expression right here. So we know that it goes as CA squared with a minus sign. So RA is a function of CA with something like this. Minus C, did I get that right? No, the rate RA is negative. So as a function of CA. So, and it goes quadratic. So it looks something like this. So as the concentration goes up, the rate speeds up, and I deplete A faster. Well, this is a nonlinear function. What I can do sometimes it's useful, is I can say, let's say I start out here. Let's say this is my CA in. If CA doesn't change much, then maybe I can approximate this by a straight line, by the tangent of the curve. And if I approximate it by a straight line, the tangent to the curve, then the tangent is a linear function. So in that case, I'm back to this, where I know how to solve the equations. Now, you can imagine that if I don't go too far from CA in, it's not so bad. But obviously, if the concentration changes a lot from CA in, it's really bad far away, but it's pretty good close. So that's the notion of linearization. And how do I know how to act? Let's define what linear is first, and then we'll see how we get the tangent to the equation. So a linear function, L of x is linear. Definition, if for any constant C1, C2, L of C1x 1 plus C2x2 is equal to C1 L of x1 plus C2 L of x2. That's exactly the definition of what linear means. Linear means if I multiply x by a constant, I multiply the answer by a constant. Linear means if I take x1 and x2 and I add them, and I take L of the sum, that's the same thing as the sum of the elements. So this is the definition of linear. And how do I know how to linearize? Well, luckily, Taylor from Taylor series told us how to linearize. So we need to remind ourselves about Taylor's theorem, which you had in calculus. So let's recall what Taylor's theorem is. Taylor's theorem says if suppose f is a function from R to the m of R. So that means the domain could have many dimensions, R to the m, but we're going to take a simple case where the range is just one dimension. And I'm going to suppose that it is m times, not m, n times differentiable. which I'm going to call, what do I want to call it, z0. Actually, in a circle, in a circle centered. In a circle of radius r centered at z0. So remember, I've got r to the n, so I could have the plane or 3 dimensions or 20 dimensions. And I'm assuming that near a point in that space, there's a circle, or if you like, a sphere around it, of a certain radius that the function is n times differentiable everywhere in that sphere. Then f of z can be written as f of z0 plus f prime of z0 over 1 factorial times z minus z0 plus f double prime of z0 over 2 factorial z minus z0 squared plus dot 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 plus, and let's get this right. Plus fn of z0 over n factorial z minus z0 to the n plus, now I can't go forever because I've only assumed that it's n times differentiable. N times differentiable. So here I have, and I think I need n plus 1 times differentiable, plus f n plus 1 of some z star divided by n plus 1 factorial times z minus z0 to the n plus 1, where z star is some point in the sphere. Okay, this sounds very mathematical. Why am I telling you this? The first thing is it tells me in some sphere, let's say I'm in the plane, around z0. So I have a radius of the sphere r, and I know that the function is sufficiently differentiable in this circle. Then, if let's say I'm in the plane, then f at any point in here can be written exactly, and I don't need an infinite series. I can have a sum of terms, and I know and I don't have to go forever. I can stop at any point, and I know that the term that's missing that has the rest, I can't tell you exactly where z star is, but I know that there's some z star in the circle that will make this an equal sign and not an approximate sign. And the reason that's interesting is because if I truncate, if I only keep up to here, this tells me I can estimate how big the error is, because if I know fn plus 1, the maximum value of fn plus 1 anywhere in the circle, then I know the maximum value of this. I know the maximum value of this is just a radius, and this is a number. So that tells me at any level of approximation, I know exactly how accurate. I know I can bound how big the error is. So I can estimate how big the error is. Now, let's look at the case where n is 2. Because that's going to be the one we're usually using. In particular, for n equals 2, we have that f of x, y is equal to f of x0, y0 plus f prime of x0, well, let's be careful here. So here I have the f dx at x0, y0 times x minus x0 plus the f dy at x0, y0 times y minus y0 plus y over returns. And just for fun, I'll write some y over returns. I can have d squared f dx squared x0, y0 x minus x0 squared over 2 factorial plus d squared f dy squared, y minus y0 squared over 2 factorial, plus 2 d squared f dx dy, x0, y0, x minus x0, y minus y0. And do I divide by 2 factorial? See if I remember that. No, I don't have to. And then I have plus a remainder term, where this term is called the remainder. So that's Taylor's theorem, that's being explicit. And I'm going to relate it to this picture in a second. If anyone is curious what the remainder term is, I'll just, for anyone who's particularly curious, the remainder term is 1 over n plus 1 factorial times x minus x0 to the n plus 1 f, a bunch of x's, n of them, of x0, y0, plus y minus y0 to the n plus 1, f a bunch of y's, x0, y0. And the stuff in between are these mixed partials. You don't have to fuss. You don't have to worry about this. This is just for your edification. Remember, notice if I look at second derivatives, I got second derivative with respect to x, second derivative with respect to y, and the mixed partial. If I go into third derivatives, I have more mixed partials. I've got 2 x's and 1 y, 2 y's and 1 x, etc. So the remainder term is a little more complicated. What are we using in this class? In this class, we're linearizing. So notice if we truncate here, if we only take the terms above the blue line, now of course I know exactly what the error is. I can estimate I can give you an upper bound on the error from this expression. We're usually not going to fuss about that in this class, but what does the error mean, this error term? That's telling me, depending on where I am, how bad this approximation is or how good the approximation is. Out here, the approximation is bad. Over here, the approximation is good. So this gives you a way of estimating how bad the approximation is if you choose to do so. But notice, if we use this expression, then we only have x minus x0, a constant, x minus x0, y minus y0, all in different terms. So there's never a product of 2 x's, or 2 y's, or an x and y. So if we do this, this is the linear approximation. When I have 2 variables. If I only had 1 variable, I could think of this as my linear approximation, just to be this term. If I only have 1 variable. So let's see how that works out in a problem. But are there any questions on what we're doing there? Let's calculate a few linearizations. So let's look, for example, at CA squared is my function. So CA squared, so example. So if I follow this, so what I need f prime. This is a function of only 1 variable. So what's f prime of CA if f is CA squared? What's f prime? 2CA. So this says that CA squared, so let's go to this equation here, is equal to CA0 squared, function at CA0, plus the derivative 2CA, evaluated not as but evaluated somewhere at CA0, divided by 1 factorial, well 1 factorial is just 1, times C minus C0. CA minus CA0 plus remainder. So that is the linear approximation. This is nonlinear. Here's a constant, and I just have a CA minus CA0. Clear? Let's do another one. Let's let f of CA be CA to the 1/2. What's f prime of CA? If it's CA to the 1/2. Someone, if you answer, just take your mask down. What's the derivative of, why don't I just call it x? What is the derivative, f prime of x? What's the derivative of this x to the 1/2? Well, this is high school calculus. Yep. 1 over 2 square root of x. So now that tells me that the square root of x is equal to the square root of x0 plus the derivative, 1 over 2 square roots of x0, evaluated x0, divided by 1 factorial, which is 1. I'm sorry to be so fussy about that, but I just want to follow the rule, times x minus x0, plus the remainder term. Notice the square root is nonlinear, this is linear. Why don't we do another example? Let's see. How about sine x? What's f prime of x? If f is sine x? Cosine x. So that tells me that sine x is equal to sine of x0 plus cosine of x0 for 1 factorial x minus x0. And in fact, plus a remainder. And in fact, this is what you're used to for the Taylor series, for the power series. If I choose x0 is equal to 0, if I choose x0 to 0, then that just gives me that the sine of x is equal to 0, cosine of 0 is 1, x minus x0. And if I go on, the next term will be x minus x0 cubed over 3 factorial plus x minus x0 to the 5th over 5 factorial plus dot dot dot. So here I've not only taken the linear term, I've gone to the all the way up to 5th order. But it just fits this formula. But I don't have to take x0 to 0. I can do about any x0, and then I still use this formula. Questions? Do you have a picture of this board so I can erase? And if you, in your kinetics class, you'll see that that is a form that you get often when you have what's called Langmuir-Hitchwood kinetics, or kinetics where you have something attaching to a surface site on a catalyst, but there are only a finite number of surface sites. So when they're filled up, nothing else can attach. So let's linearize that as well. So what's f prime of x? So here we have to use the quotient rule. Anyone want to volunteer and do it, or should I do it? I don't see any volunteers, but you really want to be able to do this yourself. So it's f prime g. It's numerator prime times denominator. Numerator prime is 1 times the denominator minus the numerator times the denominator prime of the denominator. The prime of the denominator is a over denominator squared. So I have ax and minus ax, so I have 1 over 1 plus ax quantity squared. So here I can write x over 1 plus ax is equal to x0 over 1 plus ax0 plus the derivative 1 over 1 plus ax0 squared over 1 factorial times x minus x0 plus the remainder. So here the only trick is being able to take derivatives, which I'm sure, as long as I don't call on you to do it, I'm sure you can do it. Any questions on that? Well, then let's go through and do a problem. Let's look at CSTR with a second order reaction. Let's do the first problem we started with. So we have the CSTR. And I've got 2A goes to problem. And I write the CSTR equation. I'm assuming constant density isothermal, and whatever else I need. So let's write out the CSTR equation. I've got dCA dt is equal to CA in minus CA. This is CA in. This is CA. Since it's well mixed, CA on the output is the same as CA in the reactor. Divided by tau. Tau is the volume of the volumetric flow rate. Another thing that looks like a T. Plus the rate of generation, plus the rate of generation. But the rate of generation is minus 2K Ca squared. So here is my CSTR equation. But this is nonlinear. But I know how to write Ca squared. We did it over there. So I can linearize. The equation. So let's linearize the equation. So this tells me dCA dt is about equal to Ca in minus Ca over tau. And now instead of minus 2K Ca squared, I've got minus 2K. And instead of Ca squared, I have some Ca reference. The point about which I do my linearization, plus the derivative, we have it over here. I don't have to pull that out of thin air, we did it. Plus 2 Ca reference over 1 factorial, just 2 Ca reference. Times Ca. Ca minus Ca reference. Third part of the blackboard there. 2 Ca ref times Ca minus Ca ref. Plus the remainder term, which we're going to ignore. So is that clear? All I did is I copied this part, and for Ca squared, I copied this. Where instead of calling it CA0, I call it CA ref, because it's the point about which I did my linearization. Now, so now let's just write out what happened before t is equal to 0. So I think the problem I want to do is I think I want to include a step change in the input. So let's assume that my input Ca in goes, at t is equal to 0, goes through a step change. Fine. And for t less than 0, the system was in steady state. So I have a reactor operating in steady state with the Ca in. And this is, of course, Ca in. And this is Ca in greater than, for time greater than 0. It was operating at a steady state for Ca in t less than 0, and then I changed it at t is equal to 0 to Ca in for t greater than 0. So here I've written out the CSTR equation for what happens when t is greater than 0. Now, just for fun, I also want to write out what happened to t equals 0. At t equals 0, the system was at steady state. So when t is equal to 0, dCA at t equals 0, dt was equal to 0 because it was steady state. And that's equal to, well, that was CA in for t less than 0 minus CA at t equals 0 divided by tau. So I'm just changing the concentration of CN, not the volumetric flow rate. And I'm going to subtract off the entire thing, minus 2K CA t less than 0 squared. So now what I'm going to do is I say, well, what reference state should I choose? That is, about what point should I do my linearization? And if I notice, if I choose to do my linearization about, so let's let CA ref be equal to CA as t less than 0, which was steady state. Now that's a choice. I can linearize about anything I like, but I decided that that might be a convenient choice. So now I can identify CA ref and CA t less than 0 are the same thing. And if I do that, I can subtract these two equations. So subtract. The t greater than 0 equation minus the t equals 0 equation. And let's see what I get. So on the left, I have ddt of CA minus CA t less than 0. Because, well, let's call t equals 0. So CA and t is equal to 0. I could bring them both inside the derivative. And this guy was 0, so it's not a problem. Now let's notice what I have here. Here I have 1 over tau, and here I have CA in t greater than 0 minus CA in t less than 0. That's this guy minus this guy. And then I subtract CA minus CA at t equals 0. This is t equals 0. T equals 0. T less than 0, that's okay. I subtract CA minus this divided by tau. And what else is left? So now I notice I have minus 2K CA ref squared, and here I have minus 2K CA t less than 0 squared. If CA t less than 0 is C ref, these terms cancel. This and this are the same. So the only thing I have left is minus 4K CA ref, which is CA of t less than 0, t equals 0, or t less than 0. Maybe I should just be consistent and always call it t less than 0 instead of switching up. Times CA minus CA of t less than 0. Okay, so let's just review what I did. I wrote out the general CSTR equation, which I then linearized. And again, the situation is for t less than 0, the system was at steady state at a particular value of CA in. And then I introduced a step change in CA in, leaving the volumetric flow rate the same. So I have the linearized equation for t greater than 0 over here, and I have the full equations for t less than or equal to 0. When I subtract them, the square term cancels. This term canceled, and I'm only left with this thing here. And I want you to notice that every variable in here comes in as a difference. This variable is CA minus its value at t less than 0. This is CA in minus its value at t less than 0. This is CA minus its value at t less than 0. This is CA minus its value at t less than 0. So to make the notation simpler, I'm going to let, and I need more board space. Let's let CA prime be defined as. Defined means colon equal sign means definition. CA of t minus CA of t less than 0, less than or equal to 0. And let's let CA in prime be defined as CA in of t minus CA in of t less than or equal to 0. And therefore, this equation just becomes dCA prime dt is equal to CA in prime minus CA prime over tau minus 4k CA t less than 0 CA prime. What do we have here? We have the ddt of CA prime. We've got the CA prime here and the CA prime here. So I can rewrite this as dCA prime dt plus CA prime times 1 over tau, this term, plus 4k CA at t less than 0. CA prime is equal to CA in prime over tau. So what happened? We linearized the equations, and what did we find? We found, and we introduced this thing which are called deviation derivatives. Nothing to do with being a deviant, it's the change, it's deviation. And notice we have an equation that is exactly of the form that we love, our favorite equation, favorite form. We have a derivative, first derivative, a coefficient times the function is equal to a forcing function. And this thing is my time, 1 over my time constant. So I have 1 over t is equal to 1 over tau plus 4k CA at t less than 0. And what you can see here is the time constant now not only depends on the volumetric volume and the volumetric flow rate of the reactor, but it also depends on the reaction and the value of the concentration before I made the switch. This is true of nonlinear reactions. If you remember, if I had a first order reaction, if the reaction were first order, recall, then 1 over t would have been what was 1 over tau plus, if you remember, in a first order reaction, I just had, instead of a minus 4 times this, I just had a minus k, which we said was 1 plus k tau over tau. So I want you to notice, in a first order reaction, the time constant does not depend on any concentrations. In the second order reaction, even though I get a linear equation, the time constant depends on the concentration before I make the step. And that's a very special property of linear equations, that they don't depend on the value of the variable at any previous time. Explicit. The time constant doesn't depend on that. And that tells me if I double the concentration, at the input, I double the answer. If the time constant depended on that, it wouldn't be that. I think we're at the end of the hour. So what we're going to do next time is we're going to take this equation and put it into the solution here. And then we'll see what we get. And we'll look at the difference between the linear equation and the nonlinear equation. Are there any questions on that? Again, I'm sorry there's a lot of math in this class. It's just the nature of the beast. So try to like mathematics. It's not my fault, it's the nature of the subject. Are there any questions?